Okay, ladies and gentlemen, we're going to talk statics today. And so we're going to talk about equilibrium of a particle. So there's a little background information we need first. But let me say this is the beginning of analyzing lots of things put together. We have to understand how one thing will stay in equilibrium, one object, a spring, cables, etc., a beam of some sort. Before we can put everything else together, we need some rules. We need some ways of understanding this to be able to work on more complex objects. So we started with vectors. That's a little bit of math background. Now we're going to start applying this stuff. Newton's first law. In equilibrium, all the forces have to equal zero. And this is a vector equation for that. There's a couple kinds of connections before we start on free body diagrams, and that's the spring. The force is Ks. Here's the diagram that goes with it. And cables, ropes and cables. When you go around a pulley, the tension on both sides of the cables is equal in the rope. If it were not, it would move. It would not be in equilibrium anymore. There is now, we have unbalanced forces. We have tensions in the cable pulling on this thing. How come it doesn't move? Well, obviously it's attached. Let's see, find my pen here. There we go. Obviously it's attached to the ceiling. And so there's a reaction force, like so, on the center of the pulley. So that the sum of this reaction force plus the two tensions has to sum to zero. But in the cables themselves, we can do the simplification. The tension in the cable is equal. And basically, most of the time, we don't care what this force is. Okay. Now I want to turn the pen off. There we go. Back to the pointer. Regular mouse. Two force members. The force has to be axial. Now this diagram shows that. If it's not axial, it will either translate or rotate. So here is a couple forces. They are not axial acting on this object. And it obviously they're unbalanced. So it'll move. It'll translate. Let's say the forces do sum to zero, but it will rotate if it's not axial. Only if the forces are perfectly axial will it stay put. Equal and opposite and axial. Here they're equal and opposite, but not axial. So just remember that. Ropes, cables, springs, and two force members as we move forward. Free body diagram, how to make it. So draw the X and Y axis. So in this case, we can draw an X-axis like so. Ooh, what a rotten axis. Okay. K is a spring constant in this case. Draw your axis on the diagram, whatever diagram you're working with. The isolated shape. So we're going to work with this shape first. Isolate it. Apply the solve method. Find the forces. There's going to be a force acting, pulling up, and of course, weight pulling down. And then at each point, what are the three forces at this point, and so on. Label each force. So mg to represent weight, or we could use the variable w. It's a common variable for weight. F, I'll call it E. F at point E. Label each force, and so on. Go through all the various forces you need. Assign variables. assign a variable equals question mark. Be sure you have variable equals value. So we're going to find the value of this in just a second. Draw arrows for the force directions, showing all forces, active and reactive. So this would be a reaction force. This is the weight pulling down. This would be, to stay in equilibrium, then there has to be a reaction force on the rope. The rope is pulling this weight up. Apply the equations. Sum of all the forces has to sum to 0. Okay. Okay, I'm just going to erase everything so that I'm not covering stuff up. Which means the sum of all forces along the x-axis has to sum to 0. The sum of all forces along the y-axis also has to sum to 0. Components are positive if directed along the x, negative otherwise. If there's a spring, use that. And if the solution is negative, then the force direction is opposite than the actual force. So let's say we draw mg like this, and we say that the force is acting down. Well, this force, Fe, negative Fe, negative mg, would have to equal 0. So Fe equals a negative mg, which means the assumed direction downward is wrong. Let's try to get the right direction starting out, but sometimes we miss it, but that's okay. All you have to do is just turn this arrow around. Oop, I erased the whole thing. Let's get the pen back. There. So the actual direction of the force would be up in this case. Next slide. Here's the problem. Here's a free body diagram. You're told the mass now. Now you know the mass. The actual weight is 58.86. 86 newtons. This is the number you'd store in your calculator memory. Be exact when you're storing it in the calculator memory. This is just to write it on paper and round it. Don't write this down on a piece of paper, then enter it in the calculator as an intermediate computation. So that's the force on the sphere, which means this Fe, it'll be in the positive y direction, positive 58.9. And again, I'm rounding the display. I am keeping the intermediate result in the calculator. And this would be the weight. It would be a negative 58.9. The reason being is that it's acting down in the negative y-axis direction. The y-axis points up. So the knot is, so here's the force of the sphere. The sum of the forces acting on the knot, this knot from the previous diagram, let's go back, there it is, this knot right here. The sum of those forces has to sum to 0, but you do have different directions. You're going to have one force going off in the positive x-axis direction. I'll draw my coordinates here. There we go. And another force going off it at an angle. So we can label it like this, and we can call this FCD. And we can call this force FCB, which is, or excuse me, yeah, this force right here. This is the axis, the y-axis. I should probably erase that because it's in the way. It confuses the diagram. I'm trying to get the eraser. There we go. Get rid of the y, get rid of this arrow because I have my coordinates over here. FCD, FCB. Directions, one more force, and I'm going to stop the video, pick up the rest of this after after the break, or maybe I won't pick it up after the break. Maybe I'll do it now. FCE, and we know we've got the 58.9. This is the force acting on the knot. The force acting on the ball that I called FE, that's positive because it's acting up. This is negative because now we're talking about a free body diagram. We're imagining the free body diagram just around the knot only, not the ball, just acting on the knot. Oops. Oh well, I'll draw it somewhere else. So this would be the free body diagram on knot alone. And of course, all the labels, FCB, FCD, and FCE. Okay. Next. There's that. Okay, now we could solve this problem. There's the free body diagram again, acting on the knot. This problem is not solved in your book. I'm going to go on to some other problems. We'll solve those, not this particular problem. This is a very similar problem, so we'll take a look at that and use this as an example to actually do the calculations. In the next video,